In this video, we're going to continue our look at reversible nucleophilic addition reactions. Another important and useful nucleophilic addition reaction is cyanohydrin formation. So the overall reaction, we have an aldehyde or a ketone, for example, and this can react with HCN to form a cyanohydrin. One problem, though, is that when we think about the position of equilibrium for hydrocyanic acid in water, well, this has a pKa of 9.1 compared to negative 1.7. Remember, this is the reaction by which we define Ka and pKa, and we need to think about how much an acid dissociates in water. And if it doesn't dissociate much, then it's a pretty weak acid. So that's what we have here, that HCN is a relatively weak acid, which means because the equilibrium lies to the left, then there's not a lot of Cn- to be able to react at a reasonable rate. So rather than carrying out the reaction with HCN as it was first written, typically it might be carried out in the first step with sodium cyanide or potassium cyanide or something as a source of cyanide ion, and then it can be treated with H3O+. This reaction is important because it's another way that we can make carbon-carbon bonds, and we have an alcohol, which means we can convert this to other functional groups, and we have a nitrile or a cyanide group, which we haven't looked at yet, but we are going to see how this can also be converted into other functional groups. So as we consider cyanohydrin formation, the net reaction is shown here. So an aldehyde is treated with sodium cyanide followed by H3O+ to give a cyanohydrin. But let's think about this mechanistically. How does this work? Well, cyanide acts as a nucleophile, shares its electrons with the carbonyl carbon, pushing these electrons up onto the oxygen, giving this intermediate. And then with aqueous acid workup, the oxygen can grab a proton from H3O+, push those electrons onto water, and we form the cyanohydrin. Now, there's a biological example that I wanted to mention. So millipedes and certain beetles have this cyanohydrin. And think about, now we're going in the other direction, we're starting with a cyanohydrin, and so this is in equilibrium with benzaldehyde plus HCN. So hydrocyanic acid is a toxin. Now, it's favored for the equilibrium to be this way, but in the presence of a particular enzyme, the equilibrium can be pushed toward the right as written. So the cyanohydrin and the enzyme are stored separately, but then if the millipede or the beetle is faced by a predator, then these will be combined, which will make benzaldehyde, but more importantly, it makes the hydrocyanic acid, and so this can be used as protection against predators. The next category of nucleophilic addition is acetal formation. So for this reaction, we are using an aldehyde or ketone. This can be treated with an alcohol, typically in the presence of H+, to form what's called a hemiacetal. So hemi, think hemisphere. This is half of an acetal. But the hemiacetal, this is analogous to the other examples we've seen before of the hydrate of the cyanohydrin. But this will undergo a reaction with another equivalent of alcohol still under acidic conditions to give what's called an acetal. So the acetal, we have our carbon that used to be the carbonyl carbon now connected to an OR and an OR. So one important thing to keep in mind is that when an aldehyde or ketone is being treated with an alcohol, it's necessary to use two equivalents of the alcohol to form the acetal. Here's another example where we are using a diol. In other words, we have two equivalents of the alcohol within the one molecule. So this aldehyde can be treated with a diol in the presence of acid to form this cyclic acetal. then finally, we have a biological example. So many sugars are going to exist both in the linear form and in a cyclic form. And in the cyclic form, we typically have hemiacetals, right? With a hemiacetal, we have a carbon that is connected to an OH and an OR. So carbon 2 is what used to be the ketone, and here it exists as the hemiacetal. So it is this OH that reacts at this carbonyl carbon to form the hemiacetal at carbon 2 of fructose. So what's going on? If we look at the overall reaction, we have the aldehyde reacting with alcohol and H+ to form the hemiacetal, followed by a second equivalent of alcohol to give the acetal. So how does this work? Well, when we have alcohol and H+, we have protonated alcohol. So the aldehyde can act as a base, grab off a proton, put these electrons back onto the alcohol, and that gives us the protonated aldehyde. Our alcohol is not a really good nucleophile, but now that this is protonated, this is a much better electrophile. So the alcohol can add here, pushing these electrons up onto the oxygen, giving this intermediate. Now the alcohol can act as a base, grab off a proton, put these electrons onto the oxygen, giving us the hemiacetal. Next, in the hemiacetal, the oxygen of the OH can grab off a proton, put these electrons back onto the oxygen, and that would give this protonated species. Now keep in mind, it's also likely for this oxygen to grab a proton, and that is going to happen, but that would just be the reverse of this reaction. Next, water is going to steal these electrons and leave, giving this carbocation. Now, this is a relatively stable carbocation because we can draw another resonance structure that looks like this. So we have a positive charge on an electronegative element, but everybody has an octet, so this is an important resonance contributor. Next, we can consider the nucleophilic addition of a second equivalent of the alcohol, giving us this intermediate. And then finally, one more equivalent of alcohol can grab off a proton, put these electrons back onto the oxygen, giving us the acetal. Next, let's consider a useful application of acetals. Now, if we have an aldehyde and we treat it with a Grignard reagent, we know that the Grignard can act as a nucleophile. We're going to get this as an intermediate, etc. But if we were to convert this aldehyde into a cyclic acetal, or any type of acetal, this example is a cyclic acetal, and then we treat this with Grignard reagent, we're going to get no reaction because this behaves like kind of like an ether. So there will be no reaction with base, with an organometallic reagent, no reaction with a hydride, but it does react with H+ in the reverse of acetal formation. So this gives us an opportunity to protect and deprotect a particular functional group if we don't want it to undergo reaction under a particular set of conditions. To be able to use a protection-deprotection strategy, we need to make sure that the protection-deprotection is reversible. So how can we control whether the reaction goes to the right or to the left? We can use Le Chatelier's principle. So if we want to push the equilibrium to the right, then we would use excess of the alcohol. If we want to push the equilibrium to the left, as it's written, we would use excess water. So this gives chemists a way to interconvert a functional group into a different functional group that's not reactive, and to recover the original functional group back again. So here we have an example of using an acetal as a protecting group. So let's say we're starting out with this compound where we have an aldehyde and an ester. And we want to reduce the ester in the presence of the aldehyde to form this compound where we have an aldehyde and an alcohol. But we can't do it. We don't have any methods to reduce an ester that won't reduce an aldehyde, right? We have a way of reducing an aldehyde that won't reduce an ester, but not the other way around. But what if we were to treat this with, let's say, this diol in the presence of H+. Nucleophilic addition works on aldehydes and ketones, not on esters. So that is going to convert this. The ester remains intact, CH2, CH2, CH, but now this has been converted to the cyclic acetal. Next, we can treat this with lithium aluminum hydride followed by water, and I'm going to have to write this down here. So that is going to convert this into a CH2OH group, which is connected to a CH2, connected to a CH2, connected to the CH, that is the cyclic acetal. And now we can convert this to our target because we can deprotect the cyclic acetal by treating this with H+ and water to do the reverse of acetal formation. So we are protecting one functional group and then carrying out the desired reaction and then deprotecting to restore the functional group. So I just wanted you to see an example of using an acetal as a protecting group.